In this second module about Mount St. Helens, we'll pick up after the end of the dome-building eruptions in 1986. As you already know, deep earthquake activity resumed in the late 1980s, which suggested that the magma chamber beneath the volcano was pressurizing. This was a good indication that the volcano remained active and might erupt again. Some deformation measurements were made using EDM surveys, electronic distance measurement, centered on the mountain and across the region, but there wasn't any obvious inflation of the volcano. The first continuous GPS station was established on the north side of the volcano in 1997, and a network of campaign GPS stations was established around the volcano in 2000 and remeasured in 2003. None of these measurements showed any indication of pressurization. The photo here shows the continuous GPS station, which is installed on the roof of a visitor center about 8 kilometers from the volcano's crater. The data show how the station moved between 1997 and 2004. The radial measurements indicate the motion toward or away from the volcano, whereas the tangential data are perpendicular to that direction. Vertical shows how the station moved up and down. If the volcano were inflating, we would expect to see an increase in the radial and vertical trends, but both data sets are basically flat, so there was no broad-scale deformation of the volcano during this time. On September 23, 2004, a small earthquake swarm began at the volcano. The seismicity peaked a day later and then started to diminish. By September 25th, the rate of earthquakes was much decreased, but the size of the earthquakes was larger than it had been during the previous 2 days. The rate of earthquakes increased again on September 26th, gradually accelerating over the days that followed. An analysis of the seismicity showed that during late September, the earthquakes were getting shallower. The seismicity included both volcanotectonic and low-frequency events, and it was interpreted as a sign that magma was rising beneath the volcano's crater. A few days after the onset of the seismicity, a welt was noticed in the glacier within the crater of Mount St. Helens. The welt was characterized by uplift and heavily fractured ice and rock debris, and was immediately adjacent to the lava dome that formed between 1980 and 1986. A GPS station was located on that old lava dome, but it suffered a power failure in January of 2004. It was reactivated on September 27th, and since January had moved 20 centimeters away from the center of the crater and 12 centimeters up. The formation of the welt and the deformation determined from GPS was clear evidence that magma had reached very shallow levels beneath the summit crater. The presence of shallow magma was confirmed on October 1st, 2004, when a small steam explosion occurred. Coincidentally, a helicopter overflight was in progress at the same time and managed to capture video of the event. The explosion took place from the welt and was probably a result of rising magma causing groundwater to flash into steam. The eruption lasted only a few minutes, but clearly signified a new phase in the activity of Mount St. Helens. Deformation at the GPS sites located around Mount St. Helens crater was finally detected a few days after the start of seismicity. This is a continuation of the time series from the GPS station located on the roof of the visitor center. In late September, both the radial and vertical deformation trends showed decreases, which indicates that the station moved down and towards the volcano, but only by 1 or 2 centimeters. This deformation is consistent with deflation. As soon as the eruption started, continuous GPS stations were quickly established all across the volcano. Although the displacements were always very small, only 1 to 2 centimeters over the course of the entire eruption, the data suggested depressurization of the magma chamber about 6 to 10 kilometers beneath the surface. Thus, the far-field GPS sites recorded deflation of the deep magma system, while GPS stations in the crater and the growth of the welt recorded the rise of magma to very shallow levels beneath the crater floor. About 10 days after the first steam explosion, lava appeared at the surface. Over the next 3.5 years, a lava dome grew continuously in the crater, emerging as a plug of solidified material. The first year of the eruption saw a series of spines that came to be known as whalebacks because they resembled a whale breaching the surface of the ocean. Gradually, growth of the dome became endogenous, meaning that instead of lava erupting at the surface, the dome grew from within. This activity continued at an ever-diminishing rate until January of 2008, when a lack of seismicity and the end of dome expansion indicated that the eruption had stopped. The total volume of the new lava dome was nearly 100 million cubic meters, which is about the same size as the dome that formed during the 1980 to 1986 eruption. Here's another view of the 2004 to 2008 eruption of Mount St. Helens, depicted as a series of animated digital elevation models. Growth of the lava dome in the back of the crater is obvious, as is the motion of the crater glacier. The new lava dome broke through the horseshoe-shaped glacier and pushed it aside, causing ice to flow around the 1980-86 lava dome and toward the front of the crater. The two glacier lobes eventually merged at the crater front, and they continue to move towards the crater mouth today. The intense monitoring of Mount St. Helens during 2004 to 2008 provided a number of new insights into lava dome emplacement. For example, the seismic record here, which is from November 15, 2004, depicts a series of small, repetitive, low-frequency and hybrid earthquakes, which came to be known as drumbeats because of their similarity and regularity. These earthquakes were associated with the extrusion of the lava dome, possibly indicating stick-slip behavior or crack opening and closing, as the solid plug of lava was pushed out of the ground. A number of very small, repetitive tilt events were also measured by instruments installed close to the growing dome. These events, which included rapid inflation, which is upward motion on the plot, followed by gradual deflation lasting for hours, seem to come from just beneath the vent area and might indicate cycles of pressurization and depressurization within the magma conduit. The small magnitude of the tilt means that the events would not have been detectable outside the crater, so it was important to have instruments very close to the growing lava dome. The wealth of data also motivated advances in modeling of how volcanoes work. For example, rather than treating the volcano as a completely elastic structure, which is a typical approach, models were constructed using realistic physics that accounted for such variables as friction in the conduit and the volatile or gas content of the magma. These models were able to accurately reproduce the rate of dome growth, seen in the upper right, as well as the very small deflation measured by GPS stations around the mountain, as seen in the lower right. These models actually suggest that during the eruption there was no input of new magma to the chamber beneath the volcano. This is despite the fact that the volume of lava erupted was many times greater than the volume decrease in the magma reservoir. This discrepancy is probably due to decompression and expansion of the reservoir as magma flowed out. Shortly after the end of the 2004 to 2008 dome building eruption, GPS stations detected pressure building beneath the volcano. The plot in the upper left is from the GPS station at the visitor center. The red lines indicate the start and end of the eruption. Note how the north and up displacement components show positive motion after the eruption ended. This is indicating movement up and away from the volcano, although the magnitude is only about 1 centimeter. Even if very small, the displacements still tell us quite a bit about what's happening beneath the volcano. The green lines indicate the time of tectonic slip events on the nearby subduction zone, but these only affect the east component. At the same time as the inflation, deep seismicity reappeared, just as it had after the 1980 to 86 dome building eruption. It would appear that a pressure increase occurred at the end of the 2004 to 2008 eruption, and Mount St. Helens is priming itself for additional future activity.